Thanks. Okay, everyone. I think it's our great honor to invite Professor Richard Thompson to here and give a talk today. And actually, we don't know each other a very long time. Huh? We met in last month, this month, right? And then we had a talk in the bar. Then we decided to hear a talk here. Yeah, so I just get this material from Professor Richard Thompson's website. I just read it, okay? Yeah, Professor Thompson is from Imperial College London. So he's one of the elected college councils of the Faculty of Natural Science and at Imperial College London. He was previously the head of quantum optics and the laser science research group in the physics department. So Professor Thompson's research is in the area of trapped ions and laser cooling. His group trapped individual atomic ions in penny trap and investigate how to laser cool them to ultra-low temperatures. So they use them to study interactions between laser light and individual particles with applications in spectroscopy, quantum optics, and quantum information processing. So they also study ion cooling crystals, right? Professor Thompson also has very close collaboration with GSI, and he's one of the advisors of the laser spectroscopy with trapped high charged ions at high trap. So at high trap, like hydrogen like heavy ions like bismuth will be trapped and cooled, and then the ground state hyperfine structure will be studied for critical tests of QED. So today, Professor Thompson will have a talk about this laser cooled ions in a penny trap. And let's welcome.
Thank you for the very full introduction. And it's nice that I can come because I had already arranged to visit China, and then we met at Jena, and so I invited myself to come here as well while I was here. So thank you for the invitation, or thank you for agreeing. Thank you for agreeing to have me, and it's very nice to be here. So I'm sorry for the long title of this talk, but I want to talk about two things. I want to talk about the work that I'm involved with at GSI, which is to do with, as you say, sensitive QED with highly charged ions. But I also want to talk about some of the things that we've been doing at Imperial College with single ions. And what links the two areas is that it's both laser spectroscopy. So this is what I'll do. I'll give a little bit of an introduction about Imperial College, in case you've never heard of Imperial. So I'll say a little bit about that, and then I'll talk about the SPECTRAP experiment at GSI, and what we are intending to do there. And then I'll talk in detail about the penning trap and the laser cooling. Oh, I misspelled cooling. The laser cooling work there. Then I'll talk about the stuff that we're doing at Imperial College, and I will try to make sure that I don't talk too long. So this is Imperial College. This isn't my photograph, and it doesn't really look as beautiful as that. So this is a view across London. This is Imperial College. This is our lab over here. But behind it is Hyde Park, which is one of the biggest parks in London. So this is the best view that you get of green in London, and the rest is not very green at all. So we are not very large as a university. We have about 16,000 students in total, but we come quite high in the university tables. We're usually third in the UK tables. We're always behind Oxford and Cambridge, and then we're one of the top universities after that. And there are some numbers about our place. But we have one thing that we're very pleased with is that we have lots of international students, which gives it a very good international atmosphere in the university. And we have some Nobel Prize winners going back to, so in physics we have Gabor who invented holography, and Abdus Salam, who is quite well known. He was our most recent one in our physics department, and then our mathematicians have a Fields medalist just a year or two ago. In our faculty we have the 5 departments, just with the usual natural sciences, and then some interdisciplinary institutes as well, and a number of centres which concentrate on what are referred to as global challenges, these big areas of research that cut across different areas of science. So my own group is involved with ion trap research, and we fall within this quantum optics group, which has a whole, it has 3 main areas. So one is cold matter, which is cold atoms and cold ions, and then the laser consortium is involved with short pulse lasers, very high intensity short pulse lasers and interaction with atoms and molecules and clusters. And then there's a theoretical group which is doing work in quantum information and quantum optics. So our work is within the cold matter area. And then the main things that we do, well, we're working with laser cooled ions, that's the main thing. And we're looking at the formation of iron Coulomb crystals. I won't really talk about that today, but I will just show you 1 or 2 examples at the end. We work with iron Coulomb crystals, and then the main thing that we're doing is very high resolution spectroscopy with individual ions in the trap. And I will show you some of our latest results with that. And the idea of that work is to move towards quantum information processing and quantum simulations in a penning trap. And then we have this collaboration with GSI, and that's what I will talk about first. So I've stolen some slides from one of the people at GSI, because he gave, well, you were there for his talk. He talked at Jena and gave a good introduction to this facility and to the work. So I've stolen some of his slides, and then I'll come on to talk about our contribution later. So at GSI, what they want to do is to study transitions in highly charged ions that can be used to test QED. And you can see here, if you go from hydrogen to a hydrogen-like ion, like bismuth or lead, then you can get very high fields. And here you can see, this is the sort of field, magnetic field, that you can get with a magnet. But if you go close to the nucleus in a highly charged ion, then you can get much higher fields. You can see these strengths up here. You can get higher fields, and that allows you to test different components in QED. So QED has been very, very well tested at low fields to very high precision, and the idea is to do further tests at high fields. It would be nice if we could also do that to very high precision, but as you probably know, and as I will discuss, it's not so easy to do the really high precision, but we can do interesting and useful tests of different aspects of QED by working with highly charged ions. So here, there's fine structure transitions which scale with Z to the 4th, and you can study those to get information. But what we're concentrating on is hyperfine transitions, and the reason that we're interested in that at SpecTrap is because if you go to bismuth or to lead, then this transition becomes a visible transition, so you can study it with laser spectroscopy. That's why this particular transition and these particular hydrogen-like ions are useful, is because you can use laser spectroscopy techniques to measure this transition. And normally this transition, or say in hydrogen, this transition is a very low frequency. It's the 21 centimeter line that's used in astronomy, and because it goes so rapidly with Z, it means that it goes into the visible region, and that means, as I say, that means we can use high resolution techniques to measure it. And then there's other experiments, as part of HITRAP, there's other experiments here that will be measuring Zener transitions. I won't talk about that. So here, that hyperfine transition, here there's a formula for the frequency of that transition, and it has various components that come in to tell you what the frequency is, and some of these are corrections to the simple expression, and these are fairly well known, but they're not perfectly known, and that means that the test that we can do is limited because of the interaction between the electron and the nucleus. So that's something which limits how accurately you can test QED in this system. And the advantage of it, as I say, is that in this measurement you can do a measurement with very high electric fields and very high magnetic fields, and so you can get useful information. And here's the comparison between hydrogen, where this wavelength is 21 centimeters, and then if you go to bismuth, it becomes a visible transition. Well, actually it's in the UV, but it's nearly visible. But it is accessible by lasers, so you can do a high precision measurement. And so you need to find a way of creating these highly charged ions, and obviously EBITS is one way of doing that, but the other way of doing it is to use an accelerator like the accelerator that's available at GSI. So what happens here is that you have an accelerator and you put ions into a storage ring, and then you strip them of all the electrons by sending them to a target, and then in this storage ring here you can store all the different charge states, or any charge state that you want to. But for the experiments that we want to do, we want to have the ions at low temperatures. We need low velocities, and that means that you have to take them out of this storage ring where they have hundreds of MeV energy. You have to take them out of that storage ring and slow them down so that you can put them in a trap. And the reason we want them in a trap is because then there are no Doppler effects, and we can do a high resolution measurement. And so this is the HITRAP beamline, which is being developed at GSI, and it's essentially an inverse accelerator. So it takes ions from the ESR, which have been reduced to 4 MeV. It takes those particles and slows them down, and it should put them into a trap here at just a few keV, and then in this trap they're cooled right down to 4 Kelvin, and then they're transported to various experiments. And the experiment that we're involved with, the SPECTRAP, is one of the experiments here, and there are several others which I won't discuss. And the other way that we can get ions into this beamline is starting from an EBIT, and they're putting together an EBIT there as well. So that's an alternative source to give. Actually, that's to go straight to these experiments. But the EBIT isn't able to generate all the charge states that we can generate here in the accelerators. So the EBIT is good for some experiments that we will do over the next few years. But once the HITRAP beamline, this thing here, once that is available, then that will be more useful, because that will give us the very highly charged ions that we want for the QED experiment. So HITRAP was meant to be completed about 5 years ago, and it's still being constructed now, and it's not going to be available still for a few years. So this has been a much more difficult, building this it's really this decelerator here has been a much more difficult project than they expected. So, and they had funding difficulties as well. So this is not yet ready, but it's still being constructed. And this is some of the sorts of things that we could do there using laser spectroscopy on different sorts of highly charged ions. And you can see these are different sorts of transitions. So this is a fine structure transition, and then this is hydrogen-like transitions, and then this is lithium-like transitions in the same nucleus here. And if we do this measurement, if we can measure the ground state hyperfine structure in both hydrogen-like bismuth and lithium-like bismuth, that will allow us to eliminate some of the uncertainties that come in from the interaction I talked about between the electron and the nucleus, and that means that we can combine two measurements to get a better test of QED that we can get from either of these measurements on their own. But you'll see the wavelengths here are difficult, because this one is right at the UV end of the visible, and this is at the infrared end of the visible. So they're both rather difficult to work with, to have good lasers and good detectors. So this is technically quite a challenging experiment. And this is, okay, so this is the spectrum. Yes?
Why you like bismuth?
The
laser is not difficult.
Yeah, but it's because you can do this. It's the only one. It's the only one where you can get both of these wavelengths to be not too bad. So if you go to the problem is that because this is lithium-like and hydrogen-like, there's always a ratio of something like 8 between the two wavelengths. No, it's not. Well, it's more like 6 here, and so you're never going to get them both visible. There's always one is going to be to the infrared and one is going to be to the ultraviolet. So this is the one that's most accessible out of all the possibilities.
I think it's the only one.
It may well be the only one.
All this program is all
Yes,
maybe.
Holmian. Yes, I'm not sure. I've got a feeling that might be that this one might be even further into the infrared. It's a pity the way it works, so that there's very little choice.
Just the best, or
Yes.
the best.
It's the best of a bad bunch. And the other one that we are interested in is the lead one, and this isn't quite so bad because it's just 1 micron. That's not so bad, but you can't do the 2 measurements with that. So this is the spectra setup. So there is it's basically a penning trap in a magnet here, and then a laser beam that goes through the trap, a detector over here, and then ions will come in either from the high trap beam line or from the EBIT this way, or they could come from a local source. And the reason that we are putting magnesium ions in is because we can do laser cooling with magnesium, and the idea is that we would load into this trap both singly charged magnesium, which we can laser cool, and the highly charged ions, which are then sympathetically cooled by interacting with the magnesium. So you would have 2 species in here at the same time. And the experiments that I will talk about are experiments where we're working with the magnesium to get the laser cooling optimized. And once we've done that, then we will do experiments loading ions initially from the EBIT, but using the magnesium to cool them. Then this is a photograph of the setup. This is the beam line coming in from the EBIT. This is the magnesium source, and this is the magnet down here. And then the laser is underneath in a room underneath the whole assembly of that. So that's the magnesium ions coming in. That's from the EBIT, and then this is the laser beam. This is the people who who've done the work I've been talking about. So the two PhD students there are Stefan and Tobias. And Zoran is now a postdoc there, and the pretty slides that I've been using are his. So I need to give him credit for the slides. And then the ones like this, which are ugly, are my own slides. So let me talk a little bit about the penning trap, because that's what we're concentrating on here. But I will go through it quickly because I'm sure it's familiar to you. So we want to use the penning trap to hold ions for a long period of time under very stable conditions. And for many experiments like that, people use RF traps, but the penning trap has some advantages compared to the RF trap. And it has a whole bunch of applications here in these different sorts of areas. And the advantage for the work that we want to do here is that you can get a cold and dense cloud of highly charged ions in a penning trap, and in a radio frequency trap you wouldn't be able to get that, because you can't get the density and the cold temperature without micromotion, and the micromotion is a problem because it broadens the spectrum, and we want to have a narrow spectrum in order to get high resolution. So for various reasons, an RF trap is not good and a penning trap is better. And the way this works is we have electrodes, there's a ring electrode, and then there are two end cap electrodes, and we apply a DC potential between the electrodes, and then that will trap ions in this vertical direction, but they're attracted out in the radial direction, and they will hit this ring and be lost. So then the magnetic field is added, and the magnetic field will then stop ions being lost, because it just makes them go into orbits within the trap. And I want us to talk about the comparison between doing the sorts of measurements that we're talking about in a beam on fast ions in a beam, and doing it in a trap. So this experiment is actually with the bismuth, and it's a spectrum taken in the storage ring. What's happened here is that because the ions are going in the storage ring and are going fast, the Doppler effect can be used to bring the transition into the visible region here. So this is the transition we were talking about, the lithium-like bismuth transition. But because it's in the storage ring, you can use the Doppler effect to bring it into the visible. So then this is a good laser to use at around 600 nanometers, and is easy to operate. And so you can get a nice spectrum here. But the problem is that if you want to do an accurate measurement of the wavelength, you can measure it accurately here, but in order to convert it into the wavelength in the ion's rest frame, you need to know how fast the ions are going, and it's very hard to do that calibration accurately enough. So you need to have a very precise calibration in order to get a precise measurement of this wavelength in the right frame. And that's the limit currently on interpreting these results, is getting that calibration right. And also the spectrum is quite broad. If you look, it's 44 gigahertz, it's quite a broad spectrum. And what we can do in the trap is the velocity is then very low. Well, it's effectively zero, and that means that there's no Doppler broadening and there's no Doppler shift. So this width here will become about 30 megahertz rather than 40 gigahertz. And also there's no Doppler shift, so you don't need to do any calibration. But the downside is that the signal is then very weak, and the laser is more difficult for the reasons that I said. So this is what the experiment would look like. First of all, you load the ions for sympathetic cooling, and that's the magnesium here. And then you need light at 280 nanometers to laser cool the magnesium, and then that goes down to a few millikelvin temperature. Then, once you've got that cold, you then put the highly charged ions in, and the highly charged ions will cool by interaction, just collisional interaction with the cold magnesium ions. Then you can excite them and look at and do spectroscopy on the highly charged ions. So lead is about 1,000 nanometers, as I said, and the bismuth is those other wavelengths. And then obviously you can record a spectrum, and then you can interpret that to give you the test of QED. But the two really big challenges are the laser wavelengths and the signal rates that you can expect. So what we've been doing at the moment is really studying the laser cooling side of it, and building up for tests that will be with highly charged ions, but not from the high trap beamline, but from the EBIT that is just being, has just been constructed there at the moment. So the highly charged ions from the high trap beamline won't be available for some years. So what we're doing is we're working on the laser cooling, and I'll show you the results of these tests. Cooling with lasers and cooling with resistive cooling in the trap. And then the future experiments that we can do that don't need high trap, I'll work on things like argon and measuring these fine structure transitions. And this is the way that the current tests work. So this is the trap. Of course, the trap doesn't look like I said with those electrodes, and that's because we've opened out the electrodes to put them into a cylindrical shape, which is easier to build and easier to get ions in and out, and the laser beam in and out. So these electrodes, although they don't look like the ones I showed earlier, generate the same potential that you get if you have the hyperbolic shape of electrodes. So the way this works is that first of all, you put a high voltage on this capture electrode, which is down here, and the ions come in from the top and they bounce off the capture electrode, and before they bounce back to here, you raise the voltage on this capture electrode, and then the ions will be trapped between the two. So that means that the ions are confined in this region, and then you cool them either with the laser or by interacting with an external circuit, and that's this region here. Then when they're cold, you can then look at the fluorescence, or you can excite them and look at the effect on the motion, and then you can eject them and start again. So there's various experiments that you can do, but the main thing is that you have a period where you're loading, and then a period where you're cooling, and then a period where you're doing experiments. And here you can see an example. So here we've got, we're detecting the fluorescence on a camera, on a CCD camera, after the ions have been loaded into the trap and as they cool down. So here, initially, the cloud is diffuse, it's spread over a large area, and the amount of fluorescence is low. And then as the ions get colder and more are brought in, you get a more intense cloud and much sharper fluorescence. And so here you end up with a cold and dense cloud, very well defined with a sharp edge here. And this is at about, as I say, you expect this to be at a few millikelvin temperature. And you can measure the temperature, or you can get an estimate of the temperature by taking the laser that you're using for cooling and just scanning it slowly across the transition. So the laser cooling transition has a total width of about 40 megahertz. But that would be the full width, which would be this line shape here. What happens here is that you only see half the line shape, because here you're laser cooling, but once you reach the middle of the transition, if you go any higher, the interaction between the laser and the ions just makes them heat up and fall out of the trap. So you only see half the line shape. But if you measure this width of half the line shape and find out what Doppler width it corresponds to, and therefore what temperature it corresponds to. This turned out to be 100 millikelvin. So this is not an accurate way of measuring the temperature, but it gives you an upper limit on the temperature. It should be a bit lower. It should be more like 1 to 10 millikelvin. But you know that it's at least as low as 100 millikelvin, which is easily cold enough for the experiment that we need to do. So, so the laser cooling can be shown to give you ions that are in a dense cloud and a cold cloud. And I want to show you here, this is an example of the cloud. You'll see the cloud coming in and forming, but then something happens at the end which is a bit unexpected. So you can see the fluorescence building up. This is in real time. You can see the fluorescence building up, and you get a more and more bright cloud. And this looks like it's very stable, and it looks like it's going to stay like that. But then, in fact, you will see that suddenly it changes. There, you can see it shrinking and it spreads out, and then it's stable again now, but much lower. So there are things going on here which are not obvious. It's not clear what's happening, because there the cloud changes even though nothing was changed in the experiment. So it looked to be stable and then suddenly it changed. And it's not quite clear what's happening there, and that's something that we need to understand. And I'll show you another thing like that, which is that sometimes you can see oscillations like this. So the cloud is staying there over a long period, but the parameters of the cloud, the density and the temperature are changing. And sometimes this can be very regular. It can be quite a regular oscillation. And this is over a period of a few seconds or a fraction of a second, which is a very, very long time in terms of the interaction with the laser. So there's some very interesting dynamics going on here. But again, it's not very good, because it means that you haven't got stable conditions. So this is oscillating on its own. The laser and the trap are constant, but the cloud is oscillating. But it's a very complicated system, because the temperature changes and the density changes and the shape of the cloud changes and the rotation speed changes, and so all of these things can interact and you get this oscillation. So something that is understood better is the oscillation frequency, and you can see here the oscillation frequency of the ions as a function of voltage. That's exactly what you expect it to be, and that behaves well. So you measure this by preparing the cloud cold, and then applying an oscillating potential to one of the electrodes and looking to see the fluorescence change when the ion cloud is excited. So that behaves exactly as you expect it to. And here, this slide, I'm afraid it's very busy. But what it shows is that when you make the oscillation frequency of the ion coincide with the oscillation frequency of an external circuit, that's basically a resistor connected between the two end caps. What happens then is that as the ions oscillate in the trap, they induce voltages in the end caps, and so there's a current flowing in the external circuit, and that dissipates energy. The only place that energy can come from is the energy of the ions. So as they're oscillating, the energy is extracted into the circuit, and that means that they oscillate less and less and they slow down. And what happens here is that this is various experiments or various traces taken at different times after loading. So this black one is loading the trap and then monitoring the signal in this external circuit. And you can see it goes down. It goes down because the motion is cooling, okay? And that's being driven, the cooling comes from the external circuit. So this shows that the external circuit is cooling the ions. And at this point, the ions are still there, but there's no signal in the circuit because they're cold, okay? So this doesn't mean that the ions have gone, it just means that they're already cold. And then, say this experiment here is the same, except we've waited first, we've waited for this period before we turned on the external circuit. And then again, you see the signal going down. So the what's happening is that this isn't, that just proves that this is not a decay, but that it's the external circuit causing the cooling, because it starts from the same place, even if you wait this period here. And then this green curve is the same, waiting longer. And you can see here, right up to here, this one is after 45 seconds. You still get a similar signal at the beginning, which then decays away due to the resistive cooling. So if there's no, if the circuit is not turned on, the ions stay out here hot, but then once you turn it on, they cool down here, and again you get a very low signal. In fact, you'll see that the shape here is different from the shape here, and that's quite interesting. And I think that's to do with the energy. The initial energy is in this axial direction, and you will get thermalization in this period, this 45 seconds, all the way out to here. You'll get thermalization, and some of the energy will go into the radial motion. And so I think that's why the behavior here is different from what it is here, because that thermalization has taken place. And this is the last thing I want to show for these experiments. And this is just to show that when you have the resistive cooling and the laser cooling together, you get an interesting reaction between them. So here, after the ions are loaded, you see the circuit in the resonance circuit, the signal in the resonance circuit goes down, and that's because the ions are oscillating, and then their energy is taken out by the external circuit. But then when the external circuit makes them cold, then the fluorescence builds up, because the fluorescence is always going to be low when the ions are hot, because they don't interact very strongly with the laser because of the Doppler shift changing all the time. But then as they get cold, the fluorescence builds up because the interaction gets more steady. And over here, when the ions are very cold, then you get a very high fluorescence rate. So you can see that as the signal in the external circuit shows the ions are cooling, and the fluorescence rising shows that the ions are cooling as well. So you get an interaction between those two. Yeah.
But why there is a down, going down with the fluorescence at 14 seconds?
Here?
At
Or-
14 seconds.
Oh, this one?
Yeah.
Yes, that's interesting. This happens quite a lot in these experiments, and it might even be, is it visible on this one?
Because the ion curve is shape changes from vertical to horizontal.
No,
Like this.
it isn't that. Sorry, this is, oh no, okay. So we see it in this sort of trace as well, but it's probably over here. And what happens is that if you just think of a hot cloud, well, just think of one dimension. If it's hot and moving fast, and the laser beam is coming up like this, the interaction is very weak, so there's very little fluorescence, because the ions will be in resonance with the laser for a very short time in each cycle, okay? But they are interacting at some point, and so you get a slow cooling, and this amplitude goes down, and in velocity space, the amplitude goes down. And then you reach a point where in velocity, the amplitude is comparable to the detuning of the laser, and at that point you get a very strong interaction. But then if it cools further, if it cools down further, then it can be detuned from where the laser is. So again, again you get little fluorescence, because the velocity now is not big enough to interact with the laser. So we often see that on these traces, that even if you just have the laser fixed at one frequency, as a function of time, the fluorescence will go up, do a peak, and then come down again like this. And then if you move the laser closer, it will come up like this. So I think it's a similar effect there, but it's Ah, sorry.
Causes the asymmetry in the previous picture. The laser tuning. fluorescence.
The one with the temperature, or
The fluorescence versus frequency, laser frequency.
yes, the one I just showed. That's asymmetric because it's cooling on one side and it's heating on the other. So you only see half of the profile of the line.
Laser heating.
So
Cool.
yes, it's because laser cooling works when the ion is coming towards the laser. Every time it absorbs a photon, it slows down a little. But if you have the laser frequency on the wrong side of the transition, then it interacts more and more as it moves away, and so it just drives it into a bigger orbit, and so you see no fluorescence. So I think this bump here is related to the one that we see when we do cooling. So I want to move on and talk about some of the things that we have been doing at Imperial College, and I'll do this quickly. And what we